So as I told you in the previous video, let's try to answer the question we raised in previous lecture. So today we'll consider two topics. First we'll talk about Castigliano's theorem, which concerns about like a multiple laws, and then let's consider another way of solving statically indeterminate problems based on Castigliano's theorem. So let's begin from the Castigliano theorem. So as I told you in previous lecture, let's note that you can be written as function of both P1 and P2, where P1, P2 are external point laws, and you can write down Y1 in terms of partial U, partial P1. You can write down Y2 in terms of partial U, partial P2, and what Castigliano theorem tells us is that I'm gonna just tell you the theorem without giving you formal proof that if you write down potential energy in terms of like n multiple load, then displacement along that load direction, I mean it's really important, this is deflection along that direction is it can be written as partial u and partial j. Okay, so whatever how many point loads exist there, you can do this. Similarly, in addition to point load, if you can add up like these point moment m1, m2, and mm, and if you write down also torsion in addition to this moment and point force, you can write down the angle theta j in terms of partial u, partial mj, and the twist angle phi j in terms of partial u, partial tj. Okay, so without a formal proof, I'll just tell you that this is the proof proven by Castigliano. Okay, so today what we're gonna do is we'll just focus on the application of Castigliano theorem. So let's first consider a combined point load and distributed loading problem. So if this problem asks us to obtain the deflection at a point is the left hand, and this problem also gives us a condition that L over D is larger than 10, so that we can rely on the Euler-Bernoulli beam theory without worrying about the effect of shearing strain. So the first method to approach this problem is superposition method. So we have known solution for single point loading. We have known solution for uniform distributed loading over the entire beam. By combining these two answers, you can obtain the answer for the original problem. Okay, so this is the a classical a way of solving this problem. And second question is the application of Castigliano theorem. And it's for this problem, the superposition method is easier. But the reason why I tell you another method is that I want to give you like more options to approach and to solve the same problem. Okay, so given the same target, if you have like many different options to attack the problem, to solve the problem, it gives you better chance to obtain the solution, right? So it's important to have many options to have like a variety of weapons to attack your target point, and that will give you a lot of advantage. Okay, so based on Castigliano theorem, we can solve the same problem. First, we can obtain m as a function of p. Okay, so this problem, it's quite trivial to obtain m as a function of x, and when you write down m as a function of x, it will be in terms of p and w. Okay, and of course p and w and the location like this. Then we already know that general expression for normal stress can be written as this, because we are considering large aspect ratio problem now. If you plug in this expression, you have two choices. You can either solve this problem after doing integration and do the partial differentiation, or before doing this integration, you do insert this partial p inside this integral and perform this derivative first and do a little bit rather reduced integral. So I'd rather choose doing derivative first, because when you have mx squared, you have to have these guys squared, then you're gonna have higher order in terms of x. So I want to reduce the order of x first, then do integration. So after performing partial p, on m square, this m square has the p term and the other term is constant. So if you do this, it's same as 2m partial m and partial p. So you get rid of 2 with this, and you stay m here, and you have partial m partial p. After doing partial m partial p, it's really simple, minus x. Okay, so after performing this multiplication and performing the integral, you have the answer for YA. And if you compare this answer with the answer we obtained in previous page, they are identical as expected. Okay. Now the second example problem that we can solve with Castigliano theorem is, in addition to vertical deflection, can we have horizontal deflection? So in previous lecture, we discussed about obtaining the deflection along the vertical point. However, if you consider that and after applying this point force P, there are gonna be FBC and FAB, and because there is like a non-zero FBC and non-zero AB, and if their effect on horizontal side is not exactly cancelled out each other, you can expect there could be deflection along the horizontal direction, even though you apply force in the vertical direction. Okay, so regarding this problem, even though we don't have force along the horizontal direction, we can obtain the answer for this problem. I mean the along the horizontal direction. So the procedure is as follows. First, you consider P and Q, both of them are finite values, so that you just write down P and Q. After that, after writing down P and Q here, and you can write down FBC in terms of P and Q. You can write down FAB in terms of P and Q. After obtaining FAB and FBC in terms of P and Q, you can write down U as a function of P and Q. After that, if you do partial U and partial P, and if you do partial U and partial Q, it will be correspond to deflection along vertical direction and horizontal direction respectively. After obtaining this, if you plug in the given p value, which is non-zero, and if you plug in q equals 0, you will be able to obtain the solution for xb. And regarding this, if the deflection along x is 0, it will turn out to be 0 after plugging in q equals 0. If there exists horizontal deflection, even though there is only vertical force, you're gonna have non-zero xb, and then to check whether that's the case, we have to solve the problem. Okay, so let's solve the problem. As I told you, based on simple geometrical relationship, we can write down FBC and FAB in terms of P and Q. Okay, so after having FBC and FAB in terms of P and Q, we can rely on the expression for strain energy. Because strain energy for axial loading can be written in very simple way. You don't need the integral, because here m was constantly changing over the position. Here FBC and FAB is constant over the entire beam, so you can have simpler expression without the integral. Then after plug in this expression, and if you perform partial Q and partial P for this strain energy U, this is what you're gonna get. Okay, so regarding the details, you can do this by yourself. If you do partial Q, you're gonna have 2 will move here, and you have FBC, and you have partial FBC and partial Q, and you can do the same thing for the other terms. Okay, after obtaining these, what you can realize is, if you do partial FB, partial Q, partial FBC, partial Q, you're gonna have a simple number 0.8, and about FBC, you plug in this entire expression. Okay, then after repeating those simple practice for other 3 terms, you can obtain the full expression for FB and full expression for YB. And here what you can find is that there exists some terms correspond to P there exists even for the horizontal loading, you have expression including p. Even for the vertical loading, you have expression including q. Okay, this is somewhat expected, because even though you are applying the force in vertical direction, each load could have like axial loading along their own axial direction, and because of this axial loading, you can expect shrinkage or extension of each load AB and BC. Okay, so after finalizing the answer in terms of P and Q, and in terms of for both SB, XB and YB, then you plug in Q equals 0, and what you're going to end up is XB turns out to be negative 0.096 PL over AE, and regarding the vertical deflection, it turns out to be 0.728 PL over AE. Okay, so here the observation we can make is regarding the vertical direction, we have same answer as before. As you expect, if you plug in Q equals 0, your answer should be should converge to the answer we obtained in previous lecture. And regarding the horizontal deflection, even though the magnitude of deflection is not very large, if you compare 0.096 and 0.728, you can see that this is much larger, about 7 to 8 times larger than the horizontal deflection as expected. Still, due to the shrinkage or extension of load AB and load BC, you can have like a non-zero deflection even though you are applying force in vertical direction. Okay, so this is something you can expect out of this kind of structural loading, and you cannot ignore the deflection along the horizontal direction even though you are applying force in vertical direction. Okay, so you can see that by applying some fictitious and imaginary force to the problem, you can obtain the deflection along arbitrary direction at arbitrary point. Okay, if somebody asks you to obtain the for example, deflection at like a that direction, then what you do is you can apply a arbitrary loading R, which is unknown, and obtain the U as a function of P, Q, R, and try to obtain deflection at this point by plugging Q equals 0 and R equals 0. Okay, so that's the approach you can take. So this is a example a problem that we can solve out of Castigliano theorem. Now let's solve for even bizarre problem. Here we don't have like any point force. At least for previous example, we have point force. Here we don't have a point force at all, except this simple supported beam, simple supports A and B point. And this problem asks us to obtain the deflection at D point, this end of this uniform DC loading point, and from the Castigliano theorem. And what will be our answer? Can we obtain the answer? Answer is yes. As I told you, we can consider a fictitious force P, and so that you can obtain the moment as a function of this fictitious force P. Then you can write down the U as a function of m squared over 2ei, which is gonna be function of U function of P, because m is function of P. Then after obtaining U as a function of P, you perform partial U, partial P, so that you can obtain the deflection at D point. Then if you plug in P equals 0, and you're gonna get the answer for Y deflection at D point. Okay, so by doing so, if somebody asks you to obtain the deflection at E point, you can apply a fictitious force F at E point, and after solving the problem, you plug in F equals 0 to your solution, then you will be able to answer the original problem. So depending on what problem asked to you, sometimes Castigliano theorem gives you the easiest method, sometimes the superposition method gives you the easiest solution, sometimes the typical double integration method will give you the easiest route to solve the problem. So if you have all three different methods, you're gonna have more options to solve a identical problem. It'll not only give you more options, but it'll also help you to have a better and deeper understanding on what's going on. Okay, so with that, let me finish my discussion on Castigliano theorem, and in the next video, let's try to handle statically indeterminate problem based on Castigliano theorem.